Hello and welcome to XD Indexer training from Ormex Systems. This video will teach you how to begin programming motion. In this video, I will cover the motion table branch of the project tree. The motion table is where you program each of the 32 available motions. For applications with more than 32 motions, or that require the ability to change motions at will, Modbus TCP over Ethernet or other available Fieldbus options allow the host controller to change motions at any time, making the available number of motions virtually infinite. Let's take a look at the motion table. This screen displays in table format the values of each of the 32 motions. This is helpful as a reference and can be used to do some programming as well. To program a motion in the table, simply double-click on the field you wish to change and enter the appropriate value. For a simpler programming environment, expand the project tree on the left to reveal the individual motions. Let's use motion 0 as our example. Currently, there are 9 different motion types that can be programmed in the XD Indexer. Each type requires different parameters, so the lower section of the screen will change depending on the motion type you select. I will go through each motion type briefly. The first 4 are discrete, relative, and absolute motions. Let's talk for a minute about the difference between relative and absolute motion. Relative motion specifies a distance and direction. For example, let's say the quarterback of a football team commands the running back to carry the ball 20 yards downfield. If the line of scrimmage is at the 10-yard line, the running back would move the ball to the 30-yard line. This is a relative command, meaning, relative to where we are now, run 20 yards downfield. Because this command is relative, it can be executed over and over again, and he will continue to progress down the field 20 yards at a time. Absolute motion is not specified by a distance and direction, but instead a position on a predetermined scale. In this case, the quarterback will command the running back to carry the ball to the 30-yard line. This is not relative to the current position. So if the team is on the 25-yard line, he will only rush 5 yards. If executed a second time, the command will result in no motion. He is already at the 30-yard line. Back in motion set, we have 4 options, 2 that are relative and 2 that are absolute. The differences between the 2 relative and absolute motions is whether you want to specify a speed or a time. Move relative at speed specifies a distance, speed, acceleration, and deceleration. You can select a dwell time after the end of the move before it is considered complete. This dwell, specified in milliseconds, dictates how long to wait after the motor has come to a stop to declare the motion complete. This dwell will affect how some output functions behave, and it will create a pause in a chain of motions. A stop condition can be added, which will stop motion when the input that has been assigned the specific sync condition turns on before the programmed distance has been reached. If I change this to a move relative in time instead of a speed specification, I can specify how long the move should take to complete. If you specify a very short amount of time relative to the distance, you could see a fault that the program motion requires a speed outside the capability of the system. In this example, if motion 0 was executed repeatedly, the axis would continue to move 5 inches in the same direction over and over again. To move in the reverse direction, the distance must be made negative, like this. Now motion 0 will repeatedly move the axis in the reverse direction 5 inches at a time. If I change the motion type to move absolute in time, you will notice that the distance field is now a position field. This number is now a fixed location, and therefore, if I execute motion 0, I will move to negative 5 inches, regardless of where I am currently positioned. If I execute the motion again, I will not move because I am already at the position of negative 5 inches. I can also select a move velocity motion type. Here, I cannot specify a relative distance or an absolute position. Instead, I specify a speed, and the axis will move in that direction until the specified stop condition becomes true or the stop motion function is executed. To change the direction of the motion, change the speed from positive to negative. The geared motion types are to be used exclusively with XD indexers that have an auxiliary pacer encoder connected to them. The encoder provides a reference to which the axis is slaved. Changes in the position and velocity of the pacer encoder directly result in changes in the position and velocity of the servo motor, factoring in a specified gear ratio. Gear relative at ratio allows you to specify a distance for which the servo motor will be geared to the pacer encoder. In this example, for the next 10 inches of travel on the servo axis, the motor will move at a 5:1 ratio to the pacer encoder. When the pacer moves 2 inches in the positive direction, the servo will move 10 inches and will no longer be geared to the pacer. The master accel and decel allow the servo time to accelerate to the speed of the pacer and decelerate when the motion is complete. If gearing needs to be terminated early, the stop condition is available. The gear relative and master distance allows you to specify in user units how far the servo should move with relation to the pacer axis. The distance value is the servo distance. The master distance value is the pacer distance. Once this distance is reached, the axes are no longer geared together. Finally, the gear in motion type gives you the capability of specifying a gear ratio of encoder movement to the servo motor movement. 5:1 means that regardless of direction, the motor will move 5 times further and faster than the pacer encoder for an indefinite distance in either direction. The only way for this motion to be complete is through executing a stop motion or a stop condition specified here. The final motion type is not a motion at all. The pulsed output allows you to turn on an output on the drive. Simply assign pulse output 1 to an output like this. Then specify the length of time the pulse should be on. You can choose whether to continue immediately after turning on the pulse, or wait until the pulse has completed before continuing. You can specify an optional dwell after the pulse as well as a turn off early condition here. On the right side of the screen are additional options to control motion. By selecting When Complete Repeat, you can specify how many times this specific motion will be repeated. Check the When Complete chain to automatically link the end of this motion to the beginning of another. If you do not want the motion to stop in between moves, you can select Blend Motion and there will be a seamless transition from one move to the next. Because the transition takes place during the deceleration of the previous move and the acceleration of the next move, these values should be equal. You can also create a gating condition by using After Waiting for Condition, which allows you to trigger the next move based on a physical input. After you have chained moves together, they can be repeated for a prescribed number of times by enabling Chain Repeat and setting the number of times to repeat the chain. Finally, to make managing a large number of motions easier, you can tag each motion with a name in this box. Doing so will rename the motion in the motion tree to the left. This concludes this instructional video. For more information about how to use the XD Indexer, visit us at ormec.com.